Good afternoon, students. Today we can discuss about the N-channel JFET in the subject electron devices and circuit theory. So, what is a FET? First, we can discuss. It is a three-terminal device in which the current conduction is by one type of the charge carriers, and it consists of if it is an N-channel JFET, it consists of an N-type bar made of silicon conductors like this. We'll be having an N-type bar, and in this N-type bar, in the both other ends will be having the P-type bar. Okay, so base is nothing but the N-type, which is made up of silicon. And heavily doped P-Reg silicon is diffused on both sides of the N-type base, by which PN junctions are formed. Okay, so if the P-type silicon is used, the device is referred to as P-channel JFET, and it has three terminals: source, drain, and gate. This is the symbol for the JFET. It is having the three terminals with the gate, drain, and S. A source, S represents source, and between the terminals, gate and source, the voltage potential is VGS, and between the drain and source, it is nothing but VDS. Okay, and this represents the how the structure of the JFET. Okay, so we can discuss about the construction of the internal JFET. So based on the construction part, as I have told you, it is a N-type base, and heavily dot P region is diffused on both sides, and ohmic contacts are made at the two ends of the base called source and drain, and this gate is the space between the junctions is called the channel, and hence it is referred to as channel. Both the P-type regions are connected internally, and a single wire is taken out in the form of a terminal called the gate. So the electrical connections taken out in the form of two terminals called as drain and source. The drain D is a terminal through which electrons enter the semiconductor whenever a voltage is applied across the drain and source terminals. Channel is the space between the gates through which majority carriers pass. So this particular construction is based on the four terminals which is discussed, and as well as the channel. And the operation, there are three operating conditions. One is VGS 0, VDS is increased to some positive value, VGS is less than 0 volt, VDS at some positive value, and it will be, at last, it will be acting as a voltage control resistor. So the PN junction is kept in reverse bias condition always. It is working only in reverse bias condition. That is very, very important. And the voltage VDD is applied between the drain and source. Gate terminal is kept open. Okay. So first VGS is 0 and VDS is 0. We are not at all applying any voltage, means what happens, the voltage between the drain and source means the thickness of the depletion region is uniform. It exists as the same which whenever it is constructed, but a small flow of current gets initiated because this both are for reverse biased. Okay. Now we are going to apply VGS decreased from 0 and VDS is 0 volt. So what happens in this case, PN regions are reverse biased, hence the thickness of the depletion region increases. As VGS is decreased from 0, that means negative, the reverse bias voltage across that PN junction is increased, hence the thickness of the depletion region increases in the channel, also increases under the two depletion region makes contact. In this condition, the channel is said to be cut off. So value of VGS which is required to cut off the channel is called as cut off voltage. We see VGS 0 and VDS is increased from 0. See this diagram as per your previous discussion. It is increased and makes contact, which makes the channel to cut off. When VGS is negative and VDS is increased from 0, if a small positive voltage is now applied to the gate, the size of the depletion region region begins to increase, reducing the overall effective channel of the area. So it is increased further means it is going to reduce the overall effective area of the channel, and thus reducing the current flowing through it. It will be blocking the current. A sort of pinching effect takes place. This increase in width of the depletion region reduces the conduction of the channel, and if you are increasing further the VGS, what happens is the width of the channel increases and no more current, and the voltage at which the channel closes. At one point it closes. That point is called as pinch off, and it is the voltage at which the channel closes is called as pinch off voltage. It is essential that the gate voltage is never positive, since the channel current will flow to the gate and not to the source. It will damage the JFET. Okay, so when VDS is now VP, that is your pinch of voltage, ID becomes maximum. When VDS is increased beyond VP, the ID increases with an increase in VGS. So we can discuss about the characteristics. For the characteristics, this is the practical circuit you are going to take, representing all the meters connected and the supply given. The diagram represents. There are two characteristics which we are going to discuss. One is drain characteristics. So first, see these characteristics. VGS is 0 volt and then VDS is increased in small suitable steps. So actually drain characteristics is the relation between the VDS and ID. Okay, so you see this, you have increased, the VDS is increased in small suitable steps, corresponding drain current is recorded at each step. Similar procedure is used to obtain the curve for different value of VGS. Okay, so the saturation region or it will be having this pinch of, there are three regions. One is ohmic region, the VDS is increased from 0, therefore ID increases along OP. And the pinch off region, when VDS is VP, ID becomes maximum. And in this pinch off region, it was satisfies the Shockley's explanation, which is a equation which is given in the last. In this region only, the JFET is said to be operating as an amplifier. And the last one, the breakdown region, at certain voltage of VDS, that is at VB, the corresponding to point B, IT suddenly increases. This effect is due to avalanche multiplication caused by breaking the covalent bonds of silicon atoms in depletion region between the gate and the drain. So the drain voltage at which breakdown occurs is denoted as the breakdown voltage, and it shows there is a sudden increase in the current after that breakdown voltage. So next is the transfer characteristics. It represents the relationship between ID and VGS, and it is defined by the Shockley's equation, ID equal to IDSS into 1 minus VGS by VP the whole square. So when this curve gives the relationship between the drain current and the gate to source voltage for different values of VDS, these are also called as it is considered to be the transconductance curve, transfer characteristics. So VDS is adjusted to some suitable value and increase the VGS in small steps. When VGS is 0, ID is maximum, that is ID equal to IDSS. And when VGS is increased, drain current decreases and reaches to 0, denoted as VGS off. That is at that time ID is equal to 0 milliampere. So these are the this is about the construction and operation of your N-channel JFET. In the same case, if you have to know for a P-channel JFET, it is actually instead of the flow of electrons, it is instead of because it is of holes, because the base is made up of a P-type silicon bar. That is the actually thing. The operation of P-channel JFET is going to be different from N-channel JFET. Hope you have understand. Thank you.